Marco. I'm from Gilla. It's a pleasure to be chairing this morning session on the last day of what's been a great meeting. The meeting will continue to be great because our first speaker today is Norm Yap from UC Berkeley, and he's going to give us a few ideas for quantum simulations of polar molecules.
Excellent. Thanks.
You have control of these ones.
Thank you.
I have control over nothing.
Awesome. I'd like to start by thanking the organizers for, as Luigi said, a really stimulating meeting so far. And I'd like to thank all of you for being here, especially for a 8:30 morning theory talk, nonetheless, after all of the festivities and spritzers last night. I'd like to talk about a couple of ideas in the broad landscape of quantum simulation that my group is thinking about. And some of them are kind of specific to polar molecules, while others I think are broadly related and able to be done by polar molecules, but perhaps, kind of live within a slightly larger landscape. So you'll notice that the title for my talk has changed. There's now a couple more ideas than originally, but I wanted just to introduce some things that I found that I've recently been working on that I find particularly exciting in this landscape. Although the majority of the talk, sort of the second kind of half of the talk, will be based on two very, very recent preprints, which were done with a number of friends and collaborators, many of whom are sitting in the audience right now. Good. So let me just start with a very, very quick roadmap. The first idea I'll introduce is an idea that maybe is not quite as standard in the polar molecule simulation, quantum simulation literature, and it is something that kind of falls within the landscape of digital simulation. And there, I think I'll be asking maybe one of the most simple and fundamental questions, which is trying to understand the behavior of entanglement and the dynamics of entanglement in noisy quantum circuits. Then the latter two ideas will both fall under the slightly more standard realm of analog simulation, and there I'll talk specifically about using polar molecules to simulate a new type of topological insulator. And in that context, both of those ideas will be kind of mired within the usual realm of Floquet physics, where one thinks about looking at periodically driven quantum systems, so systems where the equation of motion comes back to itself. And the specific topological insulator I'll be talking about is an insulator called the Hopf Insulator. And one of the main goals of this talk is to kind of give some physical intuition, some very, very simple intuition for kind of what the underlying topological invariant of this insulator is, and give a reasonably nice pictorial representation there. So I think for this audience, it certainly is not needed, but the broader context of this is thinking about quantum simulations and having many, many different experimental systems starting to build up controlled blocks that are able to be ideal closed system quantum simulators. The context where there's been a tremendous amount of work by numerous people in the audience is in the context of mostly analog simulation on interesting condensed matter phases. These range from fractional quantum Hall physics to Weyl semimetals. But the first topic that I want to talk about is a much more digital idea where one really thinks about circuit-based quantum simulation. And I think we're hearing in this particular workshop that these ideas are kind of really becoming possibly near term to be implemented in polar molecules. So I think that's really, really exciting. All right, so let me lay out the question. I think it really is, follow with me, but I think it's really one of the most gorgeous questions in recent times that people have been asking. The question broadly is trying to ask about the dynamics of entanglement, and usually we ask this question in the context of closed, isolated systems where we think about unitary evolution. So we have some coupled set of degrees of freedom, we coherently evolve the system forward, and we start maybe with a system that has no entanglement between the constituent degrees of freedom, so something like a product state, and we can ask ourselves, as a function of time, how does the entanglement entropy change? So for those who aren't familiar with entanglement entropy, it's a super simple proxy for understanding if one, for example, makes a cut across a system, how much entanglement there is between the left and right-hand side of that. And I won't need anything more formal than that for this piece of the talk. But of course, and there has been a tremendous amount of interest in the context already of closed unitary evolution. People have recently been studying the case of random unitary circuits, where one takes a sort of digital quantum model and applies random 2-qubit gates and thinks about that as the coherent unitary evolution associated with the particular circuit, it turns out the reason why people work with random unitary circuits is both that they're generic and special. They're generic in the sense that the growth of entanglement that one usually expects for a typical thermalizing many bodies strongly interacting model is that entanglement grows ballistically in time. So entanglement grows linearly in time. And it turns out random unitary circuits have this kind of generic property that one finds in strongly correlated many-body systems. But it turns out random unitary circuits also have a second very specific property, which is that one can really use some of the analytic tools that one has from statistical physics to be able to analyze them, and that makes them kind of amenable to an analytic treatment. One thing I should say already at the outset is that the simulations that I'm going to be talking about in this digital piece are very far away from ground state physics. So the majority of the time when we think about condensed matter systems, we think about, oh, there's an interesting low energy gapped ground state. We'd like to simulate the Hamiltonian and cool and remove entropy from the system to get to the gapped ground state. Here we're asking a quantum dynamics question, which is really far from equilibrium, far from ground state physics. One can ask almost all of these questions at high temperature, and that's where the interesting physics is anyways. But in addition to these sort of unitary closed system evolutions, people have been interested in understanding what happens, and this is particularly relevant to the experimental context, what happens when one has an open system that has a noisy environment. So we imagine that every single degree of freedom, every qubit or spin in your system is coupled to a bath. And perhaps the simplest kind of toy model for this type of coupling that's amenable nicely to analytic treatment is imagining that at every instant in time, each of your degrees of freedom has a finite probability p of being strongly projectively measured by an environment or by you or by something. And this projective measurement then disentangles this particular degree of freedom from the rest of the many-body system. And that's kind of maybe a super simple toy model for thinking about how exactly we'd characterize evolution that has a hybrid nature. So both a coherent piece of the physics as well as a noisy piece of the physics. And it turns out the two questions that kind of arise in this context, in the open system plus noisy environment context, is of course, again, understanding how exactly the entanglement grows in time, and its sister question, which is if one evolves for a long period of time and waits for saturation between the competition associated with the unitary dynamics, so closed system coherent dynamics that's entangling degrees of freedom, and projective measurements or decoherence, which is disentangling the system, once that competition reaches a steady state, what exactly is the nature of the entanglement entropy, and in particular, is it volume law or area law? So let me be very specific what that means. So remember, I said that, entanglement entropy we think about as asking a super simple question. We have a many-body system, and we cut the system in half, and we ask how much entanglement is there between the left and the right-hand side of the system. If the amount of entanglement is very local, then that entanglement would only scale with the kind of the size of the cut. Will only scale with the boundary associated with the cut, and we typically call that area law entanglement entropy. On the other hand, if the amount of entanglement in the left and right-hand side of the system, as one increases the overall size of that system, scales as the actual volume of any of the pieces, then we call that a volume law entangled phase. So one can ask a simple question, perhaps the most natural one, which is in the steady state, which of these is the actual case? Good. So let me be very specific with the toy model that will broadly be keeping the back of our heads. We imagine an n-qubit system. This could be spins, could be rotational states of molecules, whatever we'd like. And we imagine that the first layer of the circuit corresponds to 2 qubit gates between nearest neighbors of my system. And I'm choosing these 2 qubit gates randomly. So I'm choosing them randomly from all allowed 2 qubit gates, so randomly from something called a Haar measure or a 2 design. It doesn't particularly matter the details of that, just a random 2 qubit gate. And then at every single step, for every single one of the qubits, there's a finite probability p that qubit is strongly projectively measured and disentangled. And then we continue the circuit on in a brick layer structure so that every single degree of freedom after 2 layers of the brick layer are going to be coupled to one another. So in some very simple sense, this is what people think about when they talk about trotterizing a Hamiltonian that has nearest neighbor interactions. Right? So this would be the breakdown of that type of a Hamiltonian. And in this type of a circuit, you already see three sources of kind of randomness or disorder intrinsic to the circuit. The first is that, as I said, every single one of these 2-qubit gates is a random unitary. It's chosen from some large subset. The measurement outcomes, when one projectively measures strongly, the outcome of that measurement, whether we're measuring, say, the z basis, whether the spin qubit is up or down, is a random statement. And also, the location of these measurements in this graph, as I've drawn it, are also going to be random, because each qubit at any instant in time has a random probability to be measured. Okay? So super simple model for thinking about the dynamics of a circuit that has both coherent pieces that entangle and decoherent pieces that disentangle. So it turns out there's two very, very natural, I think this is really some really, really gorgeous results coming from a set of papers from a number of groups. There's two kind of very natural intuitive possibilities for what happens. The first natural intuition is that, in fact, if you think about what's going on as a competition between this coherent and decoherent pieces, each of the coherent gates basically creates very local entanglement between these degrees of freedom. On the other hand, when I make, at every single step, I make a projective measurement on a finite number, a finite fraction of the qubits given by a probability p, and given whatever initial entropy was in that state, I imagine that that measurement should decrease my entropy by something proportional to p times the entropy of the initial state. And so this asymmetric competition, one maybe naturally expects that, in fact, for any noisy quantum circuit where one has decoherence in the circuit, or in this case projective measurements in the circuit, maybe one expects that, in fact, it's never possible to have a volume law phase, that at the end of the day, you can have entanglement over relatively long distances, but there's always a finite correlation length for the entanglement, even when you take the system size to infinity. So this kind of natural intuition, I think perhaps the most natural intuition, would suggest there's no volume law phase. But of course, it turns out the arguments are a little bit more subtle than that, and I think the broader community is converging to a slightly different answer, which I think is really gorgeous. And the answer there is, in fact, that as a function of the measurement probability, people are now moving towards the belief that, in fact, there's a strict quantum phase transition at a particular measurement probability or a particular decoherence rate, where if your measurement probability is larger than this critical probability, then one does indeed end up in an area law phase where entanglement is always local. On the other hand, if your measurement probability is small relative to this critical probability, then one's allowed to end up in a volume law phase where it turns out the entanglement is kind of macroscopic across both sides of the system. And I think it's a really interesting phase transition. So most of the time when we think about ground state quantum phase transitions between phases of matter, so I don't know, a mod insulator to some spin liquid, for example, we're usually thinking about statements about phase transitions between two different gapped area law states. But here what we're saying is, as a function of the measurement rate, the projective measurement rate, one goes from something that normally looks like ground state physics to stuff that looks like excited state physics. And that's a statement about sort of the higher energy states or the evolution of this particular quantum circuit. I think that as of yet, there's progress in this area, but as yet, there's nobody understands the nature of this particular transition. It's a particularly interesting question that maybe experiments could say something about. And I think within this context, the broad reason why people are moving towards this, there's kind of both analytic and numerical evidence for this. The numerical evidence really is working with random Clifford circuits, where people do this kind of Clifford circuit evolution and projective measurements, and they find a critical probability that's not epsilon. It's not sort of, this PC is not a very, very small number. People find that the probability rate is between 1/3 and 1/4 for random Clifford circuits. But there's also a really, really pretty analytic picture coming from the group of Adam Nahum working together with Jonathan Ruman and Brian Skinner. And there, the idea is that it's possible in a very, very simple way to pictorially think about the physics of the existence of this transition as a question about 2D percolation. So nominally, this is a one spatial dimension object that starts off in a product state. We think about time as the second spatial dimension, and we think about measurements as cuts in the circuit, and we ask a very simple question, which is whether or not those cuts in the circuit, on average, allow for percolation across this two-dimensional network. And in the situation where you get percolation, then the network is sort of cut in a meaningful way, and one only has area law physics, and limits where you don't have percolation of these cuts, one has a volume law phase. Okay, turns out this kind of hand-wavy picture is not super precise, but maybe gives some intuitive analytic picture for why one might in fact expect this transition. So in these two possibilities, we talked about kind of area laws and volume laws, and I think this existence of a phase transition as a function of a decoherence rate, I think people are starting to think is a relatively universal idea, although not tested really. And in particular, people are also asking about, what exactly is the growth rate or the dynamics of entanglement as a function of time. It turns out in the volume law phase, as you would sort of nominally expect, the entanglement grows very, very similar to most entanglement growth in strongly interacting systems. There it's ballistic. And the area law phase, it turns out the entanglement after a very, very quick kind of order one time, where the system locally thermalizes, it turns out then one saturates to a finite value of the entanglement, even as you take system size to infinity. Good. And the question that my group's been pretty interested in this context is broadly related to this claim that we sort of often hear about, and it kind of has become lore, I think, in the field, which is that long-range interactions, or the existence of long-range interactions like power laws, whether it's Coulomb or dipoles or van der Waals, makes these many-body systems with long-range interactions computationally more powerful from a quantum information theoretic perspective. And of course, this claim comes, the reason why it's become lore is that this claim comes from very good intuition. I think I was talking to Dave about this yesterday. And the intuition is that when you have very, very strongly long-range interactions, oftentimes the type of entangled states that one can naturally produce using these are broadly, they look like they're useful from the perspective of information processing or from the perspective of metrology. The classic example is, you have all-to-all interacting Ising interactions. That kind of is the basis for Hamiltonians like one-axis twisting, which is the basis for generating squeeze states, which are useful in entanglement. So there's a general intuition that, when you have long-range interactions from kind of a computational perspective, it may be easier to generate interesting entangled states. And building upon that intuition, our question is whether or not in these long-range interacting Hamiltonian systems, whether or not it's true that the distinction between volume law and area laws, for example, gets shady, whether or not there still exists a transition, or how exactly does the existence of a power law type interaction in a finite dimensional system change the dynamics of entanglement in these systems. So this is work that I've been doing with someone who's familiar to the local folks, Sunwon Choi, and my graduate student Maxwell Block. And the extension is very natural. We now think about a random hybrid unitary circuit that has the presence of gates that can be performed over long ranges. So one starts by picking a single site I, and then one chooses the site J randomly to perform a random 2-qubit gate on, but one chooses that site J with a distance that depends on a probability distribution that is 1 over R to some power law, and the power law mimics whatever we think the interaction in the system is, whether it's 1 over R cubed for dipoles or what have you. And we still intersperse measurements randomly, and now we can ask our question, which is whether or not in this long-range interacting system, one expects or sees something fundamentally different emerging. And recently we've been playing with both analytics and numerics on this problem. I don't know if this is right, so it's really a possible, very much conjectured phase diagram, but if it is, I do think that it's probably pretty universal for long-range circuits, or really Hamiltonian evolution of a many-body system with long-range interactions under the presence of extrinsic measurements, for example. It turns out this phase diagram I'm representing, let me walk through the different pieces of it. We're looking at a one-dimensional circuit with long-range interactions where the power law falls off as 1 over r to the alpha. So 1D, power law falls off with 1 over r to the alpha. And it turns out for alpha greater than 2, so for interactions that fall off stronger than 1 over r squared, we think that the physics basically reduces to the short range case where one again has a true quantum phase transition between volume law entanglement and area law entanglement as a function of the y-axis, which is the measurement probability p. It turns out there's a particularly interesting case, which is that in this long-range interacting system, one can either, in 1D, if one fixes dimension, one can decrease the range of the interaction by decrease alpha, so extend the range of the interaction. Or, of course, one can also fix alpha, the power law, and increase dimensionality. That has the same effect. In this case, we think that in between 1 over r and 1 over r squared interactions, there exists, at very low measurement probability, again a volume law phase. But as you go to higher measurement probability, we think the system actually enters a sub-volume law phase. This means that the entanglement between two halves of a system is strictly stronger than area law, but strictly weaker than volume law. And you might naturally expect, well, that seems like a pretty smooth object. The really interesting thing, and something that puzzles us, is the more we think about this problem and look at it both numerically and analytically, we actually think that it's hard to get out of this transition as a function of p in this intermediate regime being an actual sharp phase transition. So what we think is that for every alpha in this intermediate regime, there exists another phase transition between volume law and sub-volume law behavior. And of course, the nature of that transition is also not understood at all. So I think that'd be something really, really interesting to think about. And almost certainly, it's hard to make analytic progress on this. So whether or not one can make experimental progress would be really, really interesting. I think maybe the most relevant open question in the context of experiments is everything I'm talking about is pretty out there because I'm talking about measuring entanglement, which is something that is entanglement entropy, which is something that cares about reduced density matrices. Nominally, for a many-body system, I'd want to do full state tomography, which is really, really difficult. So I think maybe the natural question that we're thinking about and a number of other groups are also thinking about is whether or not there are correlation function measurements that can kind of sense this type of a phase transition without needing to measure entanglement entropy directly. There's obviously correlation functions like out of time ordered correlators that proxy entanglement and where that definitely works, but I think that it's not clear to me whether or not measuring those is any easier than directly measuring entanglement entropy in the first place. But I think that's maybe the most relevant question in the context of moving these towards a more realistic question for experiments to answer. Good. All right, so let me now turn to a question. Whoa, interesting. Let me now turn to a question which is which is more along the lines of typical quantum simulation questions in the landscape of polar molecules, which is much more of an analog type question. And here, the particular type of quantum simulation that I'd like to think about is one where the quantum control in the problem is done using Floquet physics. And here, Floquet physics has, what I mean by that is simply having a system where the equations of motion for the system return back to themselves after a period t. And in particular, in this Floquet physics, I'd like to emphasize that I think it's really important to break down the types of quantum simulations that one gets in this broad landscape into two different venues. The first is something I would broadly call Floquet engineering. And the idea is one uses, a time-dependent Hamiltonian, for example, periodically driven in time with light or microwaves or whatever type of electromagnetic radiation one's interested in. And the goal is to emulate some static phase. The goal is upon time averaging the Hamiltonian, that the system comes out looking like the Hamiltonian of an interesting static phase of matter. One usually works in the high frequency limit. This is a limit where oftentimes one's thinking about a Trotter type approximation to the physics. And that's kind of the first piece of the Hopf Insulator talk that I'll be talking about. But recently, there's also been evidence that, in fact, one can have intrinsically Floquet phases of matter, and these are situations where there is no there is no static equilibrium analog of the phase of matter that comes out of this. So there's no way to have a system that is not time-dependent or in equilibrium realize this particular phase of matter. And oftentimes one finds here that the usual difference is that the scale of the Hamiltonian, the interaction scale intrinsic to the Hamiltonian, is somehow very similar to the scale of the driving frequency. And this means that one can't naturally do perturbation theory, do a perturbative expansion as one does in the Floquet engineering case. Okay, I think maybe I'll try to focus on the first half, and we may not get to the second half. So the particular type of system we'll be thinking about is a topological insulator, which I think most of you are familiar with. The basic physics of this is we think about it as a band structure, and the physics of the band structure is that it turns out that in the bulk of this particular insulator, it looks really gapped and has insulating behavior, but of course on the surface has edge states which are conducting. So let me just walk us through very, very quickly some intuition for the type of topology that people think about when one talks about a topological insulator. So let's do a super quick case study together where we imagine having a two-dimensional system, so a two-dimensional lattice system that has two bands. And for any two-band model, we know that the Hamiltonian or the block Hamiltonian in momentum space can be written as a decomposition with respect to Pauli matrices. All 2x2 matrices have this property. And the coefficient in front of this is a normalized unit vector that lives in the block sphere. So really, we can think about this Hamiltonian as a map from the Brillouin zone, which corresponds to kx and ky because I have a two-dimensional system. As a map from the Brillouin zone, it takes in a k and gives me an n, which is a block vector that lives on the block sphere. And the super important thing here is that you naturally have kind of a two-dimensional object moving to another two-dimensional object, the surface of the sphere. And because of that, when one classifies these types of physics, the natural topological invariant that comes out is sort of a wrapping or a winding number. If you take this sheet, how many times does this sheet wrap the sphere? And it's natural to ask this question precisely because the dimension of k and the dimension of n end up being the same. It turns out the Hopf Insulator is a particularly interesting case where one has a three-dimensional system with two bands. So the Hamiltonian nominally looks identical. Two bands means I'm still representing things as Pauli matrices. But the important thing is that now the Brillouin zone, k vectors in the Brillouin zone map from one higher dimensional space because we have kx, ky, and kz. And in this case, if you think about pulling back any point on the block sphere to one higher dimensional space, you naturally get some sort of a curve that lives in the Brillouin zone. And it turns out the intuition for the Hopf Insulator is that in the topologically non-trivial phase, every 2 points on the block sphere pulled back via this map end up being linked knots. And it turns out that, of course, for the trivial case of the topologic trivial case, when you map them, they end up being two knots that are not linked together. So here it's really this particular topological insulator has a very different topological invariant, which is a linking number invariant and not a winding number or wrapping number invariant. It turns out that, broadly speaking, this map, which was originally looked at by my colleague Joel Moore and Xiao Gan, is a pretty complicated map. It turns out one requires strong spin-orbit coupling and also strong next nearest neighbor and long-range couplings. The phase structure of the hoppings for the kind of paradigm model of the Hopf Insulator looks like this. And it looks like an extremely complicated hopping model. But it turns out this particular dependence, especially in terms of the spin-orbit coupling, ends up being really natural for polar molecules. And the intuition, maybe I'll just speed forward a little bit, it turns out the intuition is that the workhorse for simulating this particular topological insulator is really using the angular momentum changing plus or minus 1 pieces of the dipole-dipole interaction, and then the model that we're thinking about, which I think is challenging but hopefully is plausible, is a model where one has multiple layers, 2D layers of molecules, and on even layers, the degrees of freedom are the ground state spin degree of freedoms are sort of the 0, 0 rotational state and the 1, 0 state, while in odd layers, they're the 0, 0 and the 1, 1. So they have 1 unit of angular momentum difference. And this means that dynamics between the layers is always driven by angular momentum changing plus 1 interactions, kind of a weird interaction to use. And it turns out that interaction ends up precisely producing the phase structure of the Hopf insulator. I think with that, I won't get into the second piece of the talk, but I'm happy to tell people about the anomalous Floquet insulator that we've been thinking about, which is really a very intrinsically Floquet version of the Hopf insulator during coffee or over lunch. All right, thanks a lot.
All right, so we have time for some questions.
Maybe you said this and I missed it, but probably did. In the first part where there's like a measurement probability, what does that mean?
That means that for every single qubit, we literally flip a coin, and if the coin with some biased coin with some probability p, and if the coin lands heads, then we measure in the z basis. We literally perform predictive measurement in the z basis, and if it lands tails, then we don't do anything. Every time step, exactly. So in the circuit, you see that there's a layer of interactions, then there's a layer of measurements where we flip one coin for every single qubit. There's another layer of interactions, we flip one coin for every qubit. So on every single... Yeah, exactly. And that makes sense. Sort of, we think about it as, the natural dichotomy. Really, that particular circuit is meant to simulate the types of things that we have in terms of Hamiltonian evolution. And the intuition is, if you evolve a many-body system using a Hamiltonian and you have some finite measurement rate, then you chunk up your system into a piece of coherent evolution at the sort of inverse rate, and then a set of measurements, a piece of coherent evolution, and then a set of measurements. So it's kind of trying to analog that.
I know, that question.
Sorry.
So,
Where?
Going back to the
Oh.
first part of your talk,
Oh, there
I
you
have
are.
a question, and apologies if you covered this in the first 6 minutes, but we were talking about this volume versus area law entanglement when we have these measurements. Are you thinking about bipartite entanglement entropy or some more sophisticated measure? Because I think if I just look at bipartite entanglement entropy, don't measurements always give me a volume law just because it's not a pure state anymore?
Yeah, so we're thinking about basically, it's a very subtle question actually. It turns out we're mainly thinking about Renyi entanglement entropy, like, second Renyi entanglement entropy. And in this case, certainly it's not a pure state, but with the question of whether or not when one traces out a piece of the system and asks how much entanglement is there between these two pieces of the system, there we're literally asking about the second Renyi entanglement entropy. But one subtlety is that if one looks at different entanglements, so von Neumann entanglement entropy or higher order Renyi entanglement entropies, it seems like the point of the transition changes, and actually it's not super clear to me yet whether or not the existence of that depends on which entanglement measure you use. I think the answer is no. I think it's robust to that, but certainly depending on kind of which entanglement you look at, the quantitative features of that transition can change.
I don't remember whether the topology, but this mapping from the druid zone, torus to sphere, is it homeomorphic mapping? Are these homeomorphic?
I might have remembered this as an undergrad, but I'm trying to remember a homeomorphic. I don't know. Unfortunately, I'm not being super mathematical. I think there is actually subtle mathematical questions about this particular map, but I don't. I neither know the answer.
I'm not sure that homeomorphic. I think continuous mapping between those two.
Okay, well, I can tell you physically how people do this, and you can maybe intuit whether or not it's homeomorphic or not. The basic statement is that, when people calculate something like a Chern number, one starts with little patches of the Brillouin zone, and one maps this patch to the Bloch sphere, and then one cycles through this entire Brillouin zone and asks whether or not these patches form an overall wrapping of the sphere. It turns out that it ends up from a theorem known as Gauss-Bonnet theorem. It turns out that this particular map ends up having to either wrap once or not fully wrap or wrap twice. There's an integer invariant that comes out of it, but it feels pretty smooth to me. But I don't know. For example, if I move epsilon in the Brillouin zone, then I expect the patch in the Bloch sphere to be epsilon away as well. There's another question somewhere.
Probably have time for one more quick question.
So you had this model for long-range interacting systems, where you then we're looking at a phase diagram, versus the power law and probability of measurement. Is there some sort of effective field theory reason why I should think of this particular discretization of a long-range interacting system as being totally general? Why is this the most general way of thinking about it?
That's a good question. So we've played with a couple. It's actually a very reasonable question. So we played with no, I didn't mean it in a bad way. It was it may sound specific and sounds but it's actually extremely. So it turns out you can, for example, do a couple of things. We can imagine a couple of modifications that'd be natural. One modification is because in any individual time step of a long-range interacting system, you have some weight of hopping a very, very long distance. You can say, well, maybe the right way to do this is really to have a time step of n steps, each of which get successfully longer range, and then a random measurement, as opposed to what we're doing, which is kind of a probabilistic random measurement. I think, because that there should be some reasonably long wavelength description, I think that they should be equivalent, but we've only checked a couple examples of this. But I suspect that details of the transition may change, but the existence or non-existence of a transition, and whether it's volume to subvolume or volume to area law, I hope that's robust, and I think it should be.
All right. Thank Norm again.